back to Science Fantastic with Professor Michio Kaku. Every week on Science Fantastic, we profile some of the most amazing developments that are enriching our lives and changing the way we see the universe. Well, today we have a noted astronomer from Cambridge University in the United Kingdom, author of a new book, The Secret Lives of Planets, Order, Chaos, and the Uniqueness of the Solar System. So today we're going to talk about, extrasolar planets in outer space and how do they compare with our own backyard. But once again, with us today is Professor Paul Murden of Cambridge University in the UK, author of the book, The Secret Lives of Planets, Order, Chaos, and the Uniqueness of the Solar System. So, Professor Murden, glad you could be on Science Fantastic.
It's a pleasure.
First question for you is, when you were a kid years ago, what steered you in the direction of science and eventually astronomy?
Well, I spent a lot of time in hospital in bed when I was a kid. I got polio, and so I was hospitalized for nearly a year. And so I spent a lot of time reading, and I became, I could say bookish, which would be a polite word, or a bit of a nerd. And I read so much about absolutely everything, and then I found that learning more about science was the most satisfying thing for me. And then, so I specialized in science more and more and more during my education at school. And at school, we had a telescope that was in the corner just off where the rest of the kids played rugby. Of course, I never played rugby, but I used to go back to this telescope in a sort of a cast iron shed. I used to go back to the telescope in the evening and use it. And there were some other kids in an astronomy society who used it, so I met them and joined their society. And there was an English popularizer. I wouldn't say he was your equivalent because he was not university-based, but his name is Patrick Moore. His books must be familiar to many of your listeners. And he took me under his wing, and I got really enthusiastic about astronomy. And then I sort of gave it up. I thought it might not be practical to earn a living being an astronomer. It might be better to try and do something safer, like being a teacher. So at university, I studied physics and maths. But then I went on a course at an observatory. And at the end of this course, this is when I was an undergraduate, about 19, 20 years old, and at the end of this, the director of the observatory had me into his office and asked what had I been doing. And at the end of it, he said, "Do you want a job?" So suddenly, the door opened up in front of me, and beyond it was this glorious future of being an astronomer and studying something that I really liked, being able to do something and be paid for it that I really would have wanted to do anyway without being paid. So that was it.
Okay,
that was my career.
I remember when I was a kid, I read a pamphlet that said, what's the relationship between baseball players and physicists? And the answer was, you get paid to do what you love. So I said to myself, wow, that's a pretty good deal, doing what I love and getting paid for it. Now, when I was a kid, my first astronomy book more or less said that our solar system was kind of ordinary. I mean, average. I mean, we have planets going in circular orbits around the sun, ho-hum. We have rocky planets toward the center. We have gas giants toward the outside. And in the universe, perhaps there are like lots and lots of solar systems just like us. Well, were we wrong to believe that we are average in the universe?
Absolutely we were. I mean, if you've only got one thing to study, our solar system, then that kind of misleads you into thinking that one thing you can see is typical, average. And so for hundreds of years, I guess, astronomers developed the idea that all extrasolar planetary systems would probably be much the same as that, because it was the only one we knew. But now we know, as you said, 4,000 extrasolar systems, and it turns out that none of them are like that. There's an amazing variety of planetary systems in the universe. And the particular architecture and the way our solar system works, our planetary system works and looks, is very unusual. They're all made up of the same sort of basic components, as you said, rocky planets and gas giants, but they can be all muddled up, and they're not in any kind of stability. The typical planetary system among those 4,000 has what's called a hot Jupiter. It's a planet the size of our own Jupiter, but it's very much closer to its star, very much closer to its sun. And there must have been something happened in our solar system which either kept Jupiter where it is or allowed it to go in to be hot and then brought it out again to be sort of cold and in the middle of everything. And there are sort of dynamic processes that take place in planetary systems. And in our solar system, one particularly violent event took place, maybe a few hundred million years after the formation of the planetary system, which wrecked the architecture that was going to develop. It probably ejected some planets out into interstellar space. It ejected them out of the solar system altogether. The most common kind of planet is what's called a super-Earth, a rocky planet that's maybe twice the mass of the Earth. And our solar system doesn't have one. It probably did have one, but it got thrown away. It got thrown away into interstellar space. And it was a matter of luck that it was that super-Earth that was thrown away and not our own Earth. I mean, it's a kind of counterfactual possibility that our own Earth would have been ejected into interstellar space, and if we managed to develop, even though we were now far away from our sun, we would now be living on an isolated, dark, lonely, completely sterile.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again with us today, all the way from England, is Professor Paul Murden of Cambridge University, author of an exciting new book, The Secret Lives of Planets, Order, Chaos, and the Uniqueness of the Solar System. You know, sometimes I teach physics to undergraduate engineering majors, and one thing that we try to impress upon our students is that in Newton's theory of mechanics and gravity, everything is predictable. Given the initial conditions, you can predict how a system will evolve millions of years into the future. But hey, when it comes to the solar system, that whole picture begins to fall apart because of something called chaos theory. So, Professor, tell us a little bit about what is chaos theory as applied to our solar system.
Well, what you teach your students is correct as far as it goes for a planetary system which consists of one planet and one sun. If you've got one planet orbiting around one sun, then everything is predictable. The planet goes around and around the sun in a way which, thanks to Newton, we can calculate, and you can predict millions of years in advance the occurrence of solar eclipses and other configurations in the solar system extraordinarily accurately. But as soon as you broaden out that model of the planetary system away from one planet to several, as, for example, in our own solar system, where we have 8 planets and innumerable smaller bodies, then the attractions of one planet on the other are extremely significant over a long period of time. And the whole mathematical system is what is called, as you say, chaotic, which means that if you start out from a starting position which is even slightly different from what you first assumed, then you get an answer to where everything's going to be, which is not just slightly different, but hugely different. You simply lose track of where everything is. And you have a planetary system that evolves in a way which is chaotic. In fact, this was first discovered a couple of hundred years ago by a French mathematician, Pierre Laplace, and then rediscovered as a system in meteorology. Everybody knows that you can forecast the weather quite accurately, a day or two, maybe a week in advance, but anything beyond that is very difficult. And the reason is because you can't know absolutely everything about the state of the weather now in order to make the prediction for the future. Every butterfly that flaps its wings in Brazil influences whether or not there's a hurricane in Florida or not. So the same sort of thing happens in planetary science, and so you get these sporadic, chaotic events in the evolution of the planetary system. And there was one such event in the evolution of our own planetary system a few hundred million years after it had formed. It ejected some planets, and it moved all the planets around. It moved Jupiter in and out. It swapped the positions of at least 2 of the planets. Neptune and Uranus got swapped over. So they're not so the planets are not in the original order that they started out from. And I think it means that, I think that's the fundamental reason why our solar system is unique. There are so many possible planetary systems. If you have these chaotic events happening from time to time, that among the 4,000 solar systems that we know, planetary systems that we know, there is nothing quite like ours. It's unique. It's got some special properties and special architecture which are random, which arose purely by chance.
Now, if you take a look at our solar system, Jupiter is our 800-pound gorilla. It outweighs all the other planets put together. But in these other solar systems that you mentioned, their Jupiter wanders. They're no longer in orbits very, very far away from the sun. Some of them could be quite close to the mother star. So the question is, first of all, why do they wander to begin with? And second of all, when they do wander, does that mean they fling smaller planets into outer space?
Yes to both of those. Yes to that question. The wandering happens in 2 stages, at 2 sort of separate occasions, 2 developments in the development of a planetary system. When a planetary system is forming, the planets are condensing out of a disk of material which is in orbit around the sun, a sort of a kind of a Saturn's ring type nebula. And the planets plow their way through this through innumerable small particles and gas. And there are slight asymmetries that turn up in the way the disturbance is made, so that there's a pull sometimes in towards the sun and sometimes outwards from it. And the big planets like Jupiter, as it would be when it was forming, are subject to a sort of a pushing or a pulling motion. And the hot Jupiters in other planetary systems have been pulled in towards their star. They migrate. The other thing happens with these chaotic events, which can move the planets outwards or inwards in sort of random places when all of the planets in the planetary system interact one with another, and you get one of these chaotic events taking place. And evidently what happened to our solar system is that Jupiter started to migrate inwards, and then it got into this chaotic condition and got pushed out again, and it's ended up where it is, and it ejected some planets and disturbed the rest of them.
Now, does this mean that we wouldn't be here, that the Earth, too, might have been flung into outer space if Jupiter wandered too close to the Earth and flung us into deep space?
The ultimate eventuality would have been a possibility. It could well have been that the Earth was ejected. Fortunately for us, I suppose, since it gives us a home, the Earth was not ejected. It found its way into the sort of mid-zone of the solar system, what astronomers refer to as the Goldilocks zone, where the heat of the sun is not too hot and it's not too cold, but it's just right, and it allows water to be liquid on our planet, on Earth, and it gives us the means by which life developed. If we had been disturbed too much away from the sun or got too close to the sun, then the water would have either turned to ice or turned to steam, and we wouldn't be here, and I wouldn't be talking to you on the phone today.
Okay, well, let's say a few things about the planets, because your book is called The Secret Lives of Planets. Let's talk about Venus, for example, which is the brightest object other than the moon. Children wish upon Venus when they say, "Starlight, star bright, first star I see tonight," and it's not even a star at all. It's a planet. However, it's a twin. It's a twin of the Earth, and by rights, it should be just like us. But Venus is a hellhole. So what happened to Venus?
Well, that's a very good question. There's a part answer to it, which is that it started off perhaps like the Earth. We could expect that the baby Venus and baby Earth probably look pretty much the same. All newborn babies look pretty much the same, don't they? So it started off on the same track. Probably there was water on Venus as there is now on Earth.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, our special guest today is Professor Paul Murden of Cambridge University, author of a new book, The Secret Lives of Planets, Order, Chaos, and the Uniqueness in the Solar System. Well, when we last left off, we were talking about the fact that if you believe in Newton's laws of motion, everything is predictable. The future is totally knowable and predictable. But boy, is our solar system unpredictable. I mean, I remember when I was a kid reading science fiction that Venus was supposed to be tropical. We were supposed to treat it like a vacation site. Astronauts of the future would unload their equipment on Venus and have a great time and blast off again. Well, the surface temperature of Venus is about 900 degrees Fahrenheit. So the question is, what happened? Why is Venus so, in some sense, unpredictable?
Well, Venus started off pretty much like the Earth, but it developed an atmosphere of water vapor and carbon dioxide, which are two greenhouse gases. And these greenhouse gases had a very powerful effect on Venus. The greenhouse gases that there are in our own atmosphere increase the average temperature of the Earth by maybe about 30 degrees. But for Venus, it's 500 degrees. And so Venus is hugely hot. And it also has a fantastic atmospheric pressure. At the surface of Venus, the atmospheric pressure is 90 times that of the Earth. It's roughly speaking the pressure that there is in the ocean at a depth of about a kilometer. So about about as deep as a submarine can go. The pressures that are pushing on the hull of the submarine would be pushing on whatever it is that you've got walking around on Venus. So you're right that these are not helpful conditions for life to stay in. There were also some massive geological events that took place on Venus. The surface of Venus is very young. It's only 500 million years old, which is not much in the life of the solar system, which is 4.5 billion years old. And the whole of Venus is covered with volcanic scenery. And there are thousands of volcanoes, literally thousands of volcanoes, tens of thousands of volcanoes, because of the volcanic activity that there's been there. And actually, nobody knows why that was. What kind of unfortunate event turned Venus from the beautiful planet, the planet that might have been like Florida, to the planet which is more like hell.
Now, recently, in the wires and the news and social media, it was mentioned that there could be the conditions for life on Venus. However, walking on Venus is no joy. The surface temperature is hotter than the melting point of lead. It rains sulfuric acid. You'd be crushed by the atmospheric pressure. So how is it possible, given that extremely hostile environment, that there could be life, maybe microbial life, on Venus? So explain, how's that possible?
Well, I think it's not clear how it's possible, but it looks like it might be possible, because the origins of these stories that you're quoting there is an exciting observation which has been made recently by a colleague of mine, Jane Greaves, who works at Cardiff University in Wales. She has discovered evidence for the gas called phosphine in the atmosphere of Venus. She used telescopes which are located on Hawaii in very dry air and clear air, which are able to see spectroscopic evidence at long wavelengths at this unique site in Hawaii, which indicate that there is this phosphine gas on Venus. Now, there are traces of phosphine in the Earth's atmosphere. It's an industrial gas, and it's released by industrial processes. But it's also a biomarker. It's released by anaerobic bacteria in swamps and in the guts inside animals, particularly inside birds. I understand that penguins are particularly involved. When this phosphine was discovered, of course, she and her colleagues immediately tried to explain to themselves why it was she was seeing that. And they frankly can't come up with an answer which is based on natural processes, except the thought that there might be some biological activity in Venus's atmosphere. Phosphorus is one of the few atoms which is known to be absolutely essential to life. And so because it's a biomarker, and clearly there's no industry on Venus to eject this material, so the only explanation which they can make fly is that it's produced by microbes. In the course of this work, she was able to make a map of where the phosphine was in the atmosphere. And the answer is it's in the upper parts of the atmosphere in the temperate zones. And so the thought is that maybe these microbes, anaerobic microbes, evolved during the times when Venus was more hospitable to life than it is now, and that the transition that Venus made from being hospitable for life to its current hellish nature must have taken a long time. Maybe the microbes had the opportunity to evolve into something which can survive even in the terrible conditions that there are, floating up in the atmosphere, circulating round and round, and evidently reproducing and living. Of course, that's all based on the fact that she can't find another explanation. And so if somebody does come up with another explanation, I guess she's going to have to rethink. But at the moment, she's giving seminars, and I went to a seminar by her only last week. She's giving seminars saying she's not clever enough to think of anything other than it's some sort of anaerobic bacteria, just like there are on the Earth.
To Science Fantastic with Professor Michio Kaku. Today we're talking about, our backyard, the solar system, which we once thought was so predictable and so ordinary. Boy, were we wrong. We now realize that our solar system, among the 4,000 solar systems that we're analyzing, in some sense could actually be unique. Now, what does that mean for the search for life in the universe? Well, with us today is Professor Paul Merton of Cambridge University in England. The book is called The Secret Lives of Planets, Order, Chaos, and the Uniqueness in the Solar System. Well, let's talk about Mars, which has captured our imagination for decades. And, of course, there's been sightings of chemicals on Mars, like methane, which seems to come and go. It's still controversial, but methane, of course, is one byproduct of organic activity. So has that held up? And also, there's apparently a lake of liquid water near the polar ice caps of Mars. Is that a game changer? I mean, liquid water on Mars, underground liquid water?
I think the discovery of water on Mars has been a major target of the NASA space program, and it's a target which looks like it's coming to fruition, to a positive conclusion. NASA has been producing evidence increment by increment that there has been liquid water on Mars, because there are water features in the geology, river systems, glacial terrain, and so on, and also soils and rocks that are only produced when liquid water is present. So Mars had water in the past, and it was a planet where you could anticipate that life might have evolved. But it's also true that Mars had a catastrophe, a natural catastrophe, a natural global catastrophic climate change, which took place in its history, when its magnetic field collapsed and allowed the sun's rays and the sun's particles to scour away the atmosphere, and that reduced the atmospheric pressure on Mars so that the water evaporated into space, nearly all of it. And there are now only traces of water on Mars in the form of ice at the polar caps, so far as we can see. But what has recently been discovered is what seems to be a large reservoir, a large underground lake under the poles. And the amount of water there is not huge. If you took all the water that there is on Mars and spread it evenly over the planet, it would only be a few meters deep. So compared to the Earth, where the water that there is on the Earth is perhaps thousands of kilometers deep, a couple of thousand, 3,000 kilometers deep. So the amount of water that there is there now is not huge. But nonetheless, the thought that there might be liquid water there in this underground reservoir protected from the solar radiations is very exciting. And so it does give the possibility that life evolved on Mars and has survived to the present day. So how would you know that there was microbial life there? Well, it'd be great if we could find some, and people have tried that, but not found it. Maybe they landed in the wrong place. Maybe they were looking for the wrong sort of life, doing the wrong sort of experiments to look for it. Lots of ways you could work your way around that negative result. But one way in which life might also betray itself is because of the emissions that it produces. And we talked a little while ago about phosphine being produced on Venus, it seems. Methane is produced on Mars. And methane is a byproduct of life, and so it's very tempting to think that maybe this is some of the positive evidence about life on Mars that we've been looking for. However, it's also true that there are possibilities about the production of methane, like, for example, of volcanic or chemical volcanic events or chemical reactions. So I think we've got to do better than just find methane. We've got to find other things, other chemicals as well. Might be interesting now to start thinking about looking for phosphine, so that Mars might turn out to be like Venus after all.
Well, we've had a number of scientists on Science Fantastic, some of them into science fiction, talking about one day terraforming Mars, turning Mars into a Garden of Eden by somehow melting the polar ice caps. Now, you mentioned that there's plenty of ice on Mars, especially in the ice caps. Well, some people have advocated maybe even using nuclear weapons to melt some of the ice. Other people think perhaps a more modest proposal would be to have solar satellites beam solar energy down to the polar ice caps to begin the process of melting them. But, well, you're an astronomer. You've looked at Mars. What do you think would happen decades in the future when we seriously think about perhaps melting the ice caps of Mars? What are your thoughts?
Well, I think it's an attractive possibility to sustain colonies on Mars. One of the major issues about space colonization is carrying along enough water for the long journey and the long expedition that you're going to make. And if you're going to plan on living on Mars sort of semi-permanently, then you've got to either make water or find quite a lot of it.
Okay, Paul, unfortunately we have run out of time. But once again, our special guest has been Professor Paul Murden, author of the book, The Secret Lives of Planets, Order, Chaos, and Uniqueness in the Solar System. So, Paul, thank you so much for being on Science Fantastic.
My pleasure.